In this video, I want to discuss one problem of the exam Physical Cosmology in part 3 of the Mathematical Tripos at the University of Cambridge from the year 2003. So it's about the bouncing cosmology and why it's actually ruled out. And the core of the problem that I want to discuss is to derive this inequality given here in problem E. So we have to derive an upper bound on the density parameter for ordinary matter given by the redshift at which the bounds of the universe occurred. And so I prepared a couple of things that we need to solve this problem, namely the Friedmann equations that are given in the problem in question B. We need to rewrite them in terms of the density parameters. Those density parameters are defined as follows. So it's the density of the ingredient, let it be matter, radiation, or vacuum energy, or whatever, divided by the critical density of the universe. And then both as measured today give you the density parameters as of today. The critical density is given by this expression where h0 is the Hubble parameter of today. And those are really important definitions in cosmology, and you should know them by heart when sitting an exam like this. So using these definitions, we can then rewrite the first Friedmann equation, which is the second one here, as in terms of those density parameters, and you get the result shown here in equation 1 in my sheet. And here I also used that the matter density scales as a to the negative 3. Then the second Friedmann equation, so the one with acceleration, that can also be rewritten in terms of matter density and the density parameter of the cosmology constant. Okay, now we have everything ready to start deriving this inequality. So in the first part of the question, we actually give a hint how to start. So we first have to define the conditions for A dot and A double dot for the bouncing. And this gives you a hint how to proceed in the derivation. So the bouncing looks as follows. So if I plot the scaling factor A against time, then a bouncing would bounce would imply something like this. So we have T star, and this relates to A star, and here we have a minimum. So it's a minimum, and therefore we need the following condition: A dot at T star equals 0. So the first derivative has to vanish, and the second derivative has to be positive. Okay, those are the two conditions. And then I can use equation 1 and set h squared to 0, because if A dot is 0, then the Hubble parameter must be 0 as well at the bounds. So this implies omega matter divided by A cubed minus then the curvature term divided by A squared plus omega lambda has to be 0. Okay. And now, okay, and this has to be, of course, at the bounds. And we also know that 1 plus c, that's the redshift equals 1 over a. And therefore it is more convenient to rewrite this equation as follows. So omega m 1 plus c star cubed minus omega m plus omega lambda minus 1 times 1 plus c squared plus omega lambda equals 0. So this is our first equation. Let me give it number 3. And now we also have to look at the second equation and write down the inequality given here. So we have negative 1/2 omega m times 1 plus c star cubed plus omega lambda is bigger than 0. So that's our other equation, or more precisely our inequality. Okay, so in order to get the inequality, so the upper bound on omega m, the strategy is to solve the third equation for omega lambda. So solve for omega lambda and insert this into equation 4. So that's the basic strategy. And for convenience, let me set a new variable x equals 1 plus c star. So it's much easier to rewrite everything. So it's omega m x cubed minus omega m plus omega lambda minus 1 x squared plus omega lambda equals 0, and we have negative 1/2 m omega m x cubed plus omega lambda bigger 0. So and now we can solve this for omega lambda, and this is a very standard algebra, so I'm just writing down the result. That's omega m x cubed minus omega m minus 1 x squared divided by x squared minus 1. Okay. And now we put this into the inequality, which we also first rewrite as omega lambda bigger than 1/2 omega m x cubed. Then we insert the result here, so we get omega m x cubed minus omega m minus 1 x squared divided by x squared minus 1 bigger than 1/2 omega m x cubed. And now we have to rewrite everything, solve for omega m basically. So solve for omega m, and we get an upper bound, and the upper bound is then just given by omega m smaller than 2 divided by x cubed minus 3x plus 2. So I'm not showing the steps in between because it's very straightforward. And now we insert x equals 1 plus c star, and we obtain 2 divided by c star squared times c plus 3. So it's also a very straightforward algebra, and then only a cubic term and a quadratic term in C remain, and then you can factor it like this. Yeah, and that's also the inequality that we have to prove. So we finish this problem. And then interestingly, if we assume that we see a quasar at c equals 6, then we can show that the upper bound on omega m would be far below what we actually observe. So we observe roughly something like omega m equals 0.3. Here it's at least 0.2. So the bouncing cosmology is definitely ruled out, at least in the form like this. So that's it.